And good evening, wherever you are in the world. My name is Damod Onkar, and today I'm going to present to you the first part of our 5-axis simultaneous milling in SolidCAM. In 2013 version of SolidCAM, we have made major changes. We have added a lot of new things into our 5-axis portfolio. We have got some very special dedicated applications like swarfing, multiblade machining, port machining, vacuum part trimming, and stuff like that. And then we have also made improvements to our existing 5-axis engine, which now can handle much complex parts much easily and with full user control. Now, since we are going to make this whole thing into two parts, I've also segregated the entire 5-axis portfolio, the product that we have, into different applications. We've got applications for aerospace, we have got applications for the automotive industry, and then we have got the application for die mold and styling. Now, what I've done basically is I've put applications that come under each of these industry into one area. For example, in aerospace, we've got this new thing coming up, just come up, called as a multi-blade machining, which is nothing but impeller machining, and it's a much easier way to program and cut impellers. Very less inputs and very high programming capability. We have also done a lot of changes to our existing 5-axis engine, and with that we can cut turbine blades, both steam as well as gas turbines, which is using the 4 and 5-axis functionality of our existing software. And then we have added a new function called swarfing, which can be used for cutting frame parts, which I'm going to show today. Walls of the frame parts can be cut very effectively using the swarfing toolpath creation in SolidCAM. In the automotive, we have added 5-axis contouring that can be used for trimming of vacuum form parts. We also have a dedicated port machining functionality for machining engine ports. And then in our existing 5-axis capability, I'll show you strategies that can machine tire molds very effectively. In the die mold, we have got some new features to cut small features with small tools which are deep into the mold. We also have 3 to 5-axis conversion. We have got super finishing using 5-axis to cut certain areas to give extremely high quality surface finish. A lot of changes to the multi-axis drilling now. It can now handle holes with different colors. You can specify colors of holes. And then we have STL machining, more used for styling, where you get the input as an STL file, and you can directly machine an STL file both in 3 and 5 axis without having to create any surface out of the STL geometry. So I'm going to start with the frame part, which is basically the swarfing. And what I have in SolidCAM is another example. So let me open that. Okay, I have this part with me, and you can see this is not a full frame component, but a part of the frame component. It's not the exact frame. What I've done is I've only taken a portion of that frame part, and what we are going to do is we are going to use the swarfing engine to cut the side walls. Because if I do a draft angle analysis of this particular part, if I edit this part and if I go into the draft angle analysis and pick the bottom plane as my reference, you can see that I have got walls with different angles. I've got this wall out here which has got a negative draft of about minus 12.8, and that's close to minus 13 degrees. Then I have a wall with a positive draft of about 15 degrees, 14.76. Then I have a fillet on which there is a blend happening between minus 13 to plus 14, almost 27 degrees of blending happening between these two walls. And then I have some walls which are straight. They have no angle whatsoever. They are straight, just 90 degrees. So we would like to cut this, because if you look in the aerospace industry, and if these walls have to be cut, they will be cut using a 3D function on a 3-axis machine. If I have to take this on 3-axis machine and cut, I'll have to put several passes to finish this. Whereas in 5-axis, I could use just the side of the tool and cut exactly this surface in just one pass, depending on how much is the material. I could all go one pass, or I could go in 3 or 4 passes. I could just finish this off. And this is what Swarf machining is going to do. It's going to help us cut this programming time, cut the cutting time almost by 70–80%, because we're just going to use single pass. Right, so let's add Swarf machining. Now, Swarf machining is a new functionality that was introduced in 2013. In fact, it has been improvised and improved from the earlier version, but it's totally new now. And the input given to swarfing is very less if you compare it with the regular 5-axis input that we need to provide in SolidCAM. We need to give a lot of construction geometries, leads, links, tilt angles, side tilts, lag angles. A lot of things have to be controlled. But with the new engine, you hardly have to give out any input into SolidCAM. First of all, the geometry. The geometry is segregated into 2 halves. One is the strategy, other one is the part definition. In strategy, by default, SolidCAM picks up the automatic strategy, which is the most effective strategy and will work in 99.9% of the cases. There could be this 0.1% of the case where you need to control it much better than what automatic is offering you. In such cases, you can use different functionality, like synchronize with the tilt lines, synchronize with the upper and lower curves, synchronize with the main direction, or use the shortest distance to determine the best possible tool path. But in our case, we're going to have automatic, and in the Swarf machining, in the part definition, I'm going to define the surfaces. My swarfing surfaces are 1, 2, 3, 4, 5, and this small area out here, this one, and this one. So I've selected about 8 surfaces in my swarfing geometry. And now let me give the name as swarfing geometry. If in case I have to reselect it somewhere else, I can just call this geometry. I don't have to select them again. And since I have got a radius and a floor surface, I'm expecting the tool to come and stop at these surfaces. Now, how do I tell that? I need to select these surfaces to tell SolidCAM that there is a floor out there which it needs to take care of. So I'm going to select the floor surfaces, which is this one, and all the fillets associated with the floor. Okay. All right. I'm going to select this and the final fillet out here. Perfect. So we are done with the selection, and this I'm going to say as bottom geometry or floor geometry, and save it. So I've selected the swarfing geometry and the floor geometry. I can keep some offset for the swarfing geometry. I can keep an offset of certain millimeter for swarfing. Maybe I'm doing a semi-finishing. I want to finish it later on, so I can keep an offset. I can also stop the tool much before the floor by giving an offset to the floor also. Let's select the tool. In this case, I have got a 12 millimeter ball nose, and the cutting length is obviously equal or more than the wall of the swarfing geometry. Let's select. Let's go to the levels. Plane height is automatically set to 50. It's taken from the coordinate system definition. I'm not going to change that. All I need to change is the entry safety distance and the exit safety distance. Earlier in SolidCAM, this was one value. Now it is separated. You can have different entry and different exit safety distance. Toolpath parameter, I don't need to change the cut tolerance unless and until you want to still tighten it or loosen it from the given tolerance. Machining side, however, is very important. SolidCAM gives us about 5 options. I could machine the left side or the right side of the surface depending on the selection of the surface. Or I could do the inside or outside of the surface depending on the normal direction. Or I could leave it to the software to automatically detect it for me. I'm going to use the inside option because I want to machine the inside of this entire surface that I selected. Tool axis control, you can see it's just a very small area. If you look at the regular 5-axis engine of SolidCAM, you get a host of tool axis control options. But in swarfing, you get very less options, and most of them are default, and you don't need to really change them. They work 100% fine. Link, obviously, I would like to give some lead in and lead out. The default, however, I'll pull up by 1 millimeter because I don't want it to go flat out. And the lead out 1 millimeter is important because I don't want it to scrape the bottom floor area. I want it to lift and then come out. Okay. Gouge check, I don't need because in swarfing, most of the areas are already checked for gouging. It's only in those special cases when you have surfaces that you have not selected. For example, there could be a bolt in between and you would like the tool to jump over that bolt, and those could be your check geometries. Right. Since we're going to do a single pass, this should be good enough, and I can hit save and calculate. If I show you the toolpath, you can see a very nice toolpath has been generated. Single pass with a nice entry and a nice exit. Now if I run the HostCAD simulation, I can show you the tool axis, how it's coming up. What is happening out here? You can see that the tool axis already is tilted. There is a lag that's already come into place. Now why this lag has come into place? This lag has come into place because it's found out the last position of the tool after it would finish this. This surface out here is influencing this angle, which is a positive 15 degrees. So that surface is actually influencing because that was the last area that it cut before it turned over onto this straight 90-degree surface. Fair enough, because as long as I don't have a problem here, because this is straight, I don't have a problem here because this area is straight out here. So that's fine. It's doing the straight geometry. Let's go to the next step. Because I want to see what happens as it approaches this corner. So when I go here, you can see what has happened if I move on to the side. That side tilt has changed considerably. That side tilt has completely changed. It is gradually coming back and becoming straight because it needs to cut this wall out here, which is a 90-degree wall. So it needs to align itself to that wall. So it has gradually moved itself into that wall. And let's see now what happens on this side, because there are two angles now coming into place. This is also almost straight. And as it moves towards the next wall, which is basically a minus 14-degree undercut, you can see that it has already started positioning itself to that wall. It's not doing a very abrupt positioning as it comes very close. It has already started positioning from few degrees onwards. It's going into the wall and does a nice turn. And let's see now what happens, because I already have a tilt on the side. Let me see what is happening on the other side. On the other side, it was pretty much straight. But as it starts approaching the other wall, you can see that it has already started tilting or changing its lag angle in such a way that it already gets the positive draft to it, and it smoothly maneuvers on that surface, the blending surface out there. And like I told you in the beginning, this particular surface is actually influencing the last position or the first position also. You can see that it's kept that angle constant to that particular wall as it comes out of the geometry. Okay, perfect. So this looks fine. Now what you can do with these toolpaths, for example, assuming that you have a lot of material left on the walls and you don't want to take this cut in one go, you could simply go out here into the roughing and use pattern layers. I can say, give me a pattern of 5 layers with a distance of 2 millimeters between each of these layers. Okay, let's hit save and calculate. If I go into the simulation and if I show you the toolpath, you can see that it has taken more than one pass. It has taken multiple passes using the same orientation on the walls to cut the wall, so that you don't have to worry about more material being removed in one pass. It's going to gradually remove the material from the walls. And you could also increase, for example, I could also put 10 passes actually, and if I do the calculation, run the simulation, you can see 10 passes actually, 5 passes radially. So you can also do this. You don't have to take a full depth in one go. You could run that depth by depth. You could morph between those two upper edge and the lower edge, and you could also do a radial cut into the material. So it's safe in every position. All right. Let's go to the next area. I want to show this because this is a very typical example, and I'll show how controls inside Swarfing help you overcome issues. So let me add another Swarf milling. Geometry. I'll define the surfaces. I'll pick the surfaces. The swarfing surface, in this case the surfaces are more because there are some bits and pieces. Okay, these are my surfaces. Floor surfaces, obviously, we're going to define. Okay, it's this one and this one out here. Right. And some small pieces, surfaces. Okay, we have selected it. Perfect. Let's click OK. I'm going to select same tool, and every other option I'm going to keep default except this one where I'm going to say machine inside. We will not do any links because I just want to show you the issue and how we fix it. Let me calculate it. Okay, if I run the simulation now, I go step by step, same thing, it's this surface is influencing the lag angle of the tool. Okay, it's done nicely. It's doing nice. Okay, it's now tilting. It's become straight. That's understandable. Okay, now there's something crazy that's happening. The tool is now trying to tilt into another direction. Its lag angle is changing, although it should not, because this wall out here where it is approaching is straight. So actually it has no reason for it to change its tilt angle. So let me see if it gets worse. It's actually got worse, and then it's now getting back on track. And then again it's trying to change its lag angle to a very great extent. And as it comes close to the wall, it's it changes its orientation very abruptly. Now, although this doesn't cause any gouging or any of that sort, this is catastrophic for the machine, because in a very short linear movement, a lot of angular movement is taking place on the head, especially if you're running on a head machine. A lot of angular movement is happening, and this can be quite dangerous. So what we have to do now, since we used automatic, it's used its own intelligence, it's used its own logic to come up with a result. What I'm going to do now is I'm going to edit, and I'm going to use another option inside called as the tilt lines. I'm going to force the swarfing to follow a certain pattern of tilt lines. Okay, let me pick the new tilt lines. I'm just going to pick the edges, reverse, okay, reverse, okay, okay, this also is okay. We're going to select about 8 to 10 edges just to make sure that we don't have any surprises. I'm going to select one of this edge, one of this edge out here, and then the remaining 2 edges in this case, this one and this one. Okay, right, now let's, sorry, let me select if I have a geometry already. Yep. Okay, I already have a geometry out here. Let me see and calculate this. Let's run the simulation again. We are more interested to see what happens in this area out here, because every other area it was fine. Okay, looks okay. Looks okay. Also looks okay. Looks okay. It's also looking okay in this because it's following these two tilt lines. It's fine. There's a change, and again there is a movement. Okay. This looks much better result than what we got in the very first instance. Now, if the result has to be even much more better, then I need to put a few more tilt lines out here to control the way the tool is going to behave in this whole area. So the tilt lines are now changing the way the tool is going to stick itself to the surface. It's controlling both the tilt and the lag angles and making it much more effective than the automatic result, which was not so good result. Right. So this was a bit about our Swarf machining, where you can use I can think of two applications in this case. One is an application where you have got the frame parts that needs to be cut. The other application is sometimes you need to cut the blade of an impeller, which has a straight cross section. Whenever there's a straight cross section, you could use swarfing to cut the entire blade in one go. All right, let's move to another area which we have in SolidCAM, the new thing that we have. And let me open the part. And this is a new application that SolidCAM has for machining multi-blade parts or impellers, basically. It's not that this particular impellers could not have been done on SolidCAM earlier. Obviously, we have done a lot of such impellers, but the amount of time and the programming methods used were completely different. We had to use a lot of construction geometry to make the tool tilt in a particular way. We had to do a lot of gouge checks to hold the tool, and then finally we used to get a result. But with a new application in SolidCAM, it's much more simple. Right. Now what we have here. Inside SolidCAM, we have got a new function called as Multiblade machining. This machining is meant for cutting parts like this, impellers like this. So let's hit the multi-blade machining, and within multi-blade machining, we have got 4 sub-options: roughing, blade finishing, hub finishing, and fillet finishing. Separate strategies for each of the areas or elements of a blade. Let's start with the roughing. Let's go to the geometry. It's pretty nicely split up. First is the strategy, 3 main strategies: offset from the hub, which is the lower surface; offset from the shroud, which is basically this small surface up here on the top of the blade; or offset between hub and shroud, which is basically morphing between the lower surface and the upper surface. Let me use that. The next I need to select is the geometry, blades, splitters, and fillets. Everything to be selected. You don't have to leave out anything. I already have some geometry selected. Let me pick that geometry. Okay, so I have selected the blades, fillets, splitters, everything. Everything is one geometry. Okay. Now it's asking me to pick the hub, which is the lower surface. If I go to the hub, I have got 2 options. One, I could pick this entire surface. Or, for SolidCAM's multi-blade machining, you need not be picking up the entire surface. You just have to pick a very small piece of that surface. SolidCAM understands that it's a surface of revolution, so I've just picked up a very small area. It's got nothing to do with this area. It is from somewhere else. I've picked that surface. So if I show that surface, that's the area that I've picked. SolidCAM understands that these are surfaces of revolution, and it creates internally its own surface of revolution. Shroud, again, I don't need to pick all the upper surfaces. I just need to pick one piece of the shroud. That's the shroud that I've picked up. Okay. And I would like to keep about 0.2 millimeters on the blade, splitters, and fillets. On the hub, I would like to keep about 0.2. Shroud, I need not keep anything. Let me pick a taper ball nose, because these are the most common tools that are used in impeller cutting. The taper ball nose, because they allow you to go with a very small radius, and yet they're very robust. Right. So we're going to use this taper ball nose. Levels, you can see everything is automatic. Auto detect dimension and position. I just have to say what kind of clearance I want to use, whether it's a spear or a cylinder. In case of an impeller, spear is the most common option used. So we're going to use spear. Toolpath parameters. All I need to define is how many cuts do I need depth-wise. So I need 10 cuts depth-wise. And how many cuts do I need on the width or on the area? I'll say I want 12 cuts in the area. So I have got axial cuts and the radial cuts. Also, I would like to start about a percentage lower than the edge of the exact surface and stop again at 1% above the exact edge. So I've got starting at 1%, ending at 99%. This is done basically so as to get a very nice cut on the edge, because sometimes if it's an imported geometry, the edge could be a little jagged and you don't end up getting good cuts on the edge. So just move it by about 1% or even 0.5% is good enough. Tool axis control. Okay, the next one here is a sorting. I would like to do a zigzag from the trailing edge. What is a trailing edge? Now, in an impeller, we have got some terminologies. For example, I explained that this was the hub, then you have a shroud, then you have the main blade, you have the splitter, you have got this as your leading edge. The bigger edge is the leading edge, and the smaller edge basically is the trailing edge. So I want to do a zigzag kind of machining with the tool starting from this side of the impeller and not from the other side. And I would like to go left to right. Perfect. Surface quality, I'm going to keep about 10 microns. And the edges, I'm going to have an automatic rolling. We are not much bothered about the edges. Tool axis control, again, a very small area. And these default values work 100% fine. We have checked it in almost several parts. The default works fine unless you really want to tinker with some value, which would probably give you a much better result. Is that what you think? In the linking is also automatic. You don't have to define anything, just click on these two buttons and the links will be done automatically by SolidCAM. Gouge check is not needed unless and until you start finding out that the tool is really rubbing on certain edge, which it should not. In that case, you can switch on the gouge check. Otherwise, the gouges are automatically checked inside while generating the toolpath. All right, let's save and calculate this toolpath. This would take about 40. It has calculated the toolpath. Now let's look at how the toolpath looks like. Remember the kind of input that we gave, minimal input, very fast, and this is our calculated result. Nice. You can see that the roughing is done very quickly, very fast, minimal input, and very high quality of toolpath. If I run my solid verification, we'll just see the upper layer, so that should be good enough of an indication of what would it look like. Okay, so we have got the roughing, and it's done a pretty neat job. You can see this is how it's going to continue the roughing all the way till the bottom. So it's done a pretty neat job in terms of roughing this part. Right, so let's come out of this. What I'll now do is I'll quickly show you how we do the finishing of the blade and how we do the hub finishing and how we do the fillets. So let me add another operation, Multiblade, blade finishing, and then the geometry. I'm going to again use the offset between hub and shroud. Now we are not going to select all the 3 blades because I just want to machine only one of these blades. So I'm going to select this as my geometry. I've already predefined. And then I have the hub, which remains the same. Face is 1, again a small piece of the hub surface, and the shroud is this. Okay. Tool, I'd like to select the same tool, the taper ball nose. I can even select some other tool. I can use a ball nose tool here, doesn't matter. Levels is automatic. Toolpath parameters, I'd like to have about 15 cuts on the surface, and I don't want it to machine completely. I just want it to machine from this edge to this edge, going all the way over the blade. I don't want the outer surface to be machined, so I'm going to say trim the trailing edge. I don't want to cut. Now you can see that the moment you select any of the parameters inside SolidCAM, it comes up with a nice image here on the left hand side. It shows you what is that parameter going to look like, or what is the influence of that parameter. Again, I would like to put the start and end percentage. Okay. Surface quality, 10 microns is good enough. Sorting, it's one way, starting from the trailing edge. Edges, again automatic. Tool axis control, I'll not touch because I'll keep it to the default values since they're working very well for me. Gouge check and linking are all automatic. All I need to do simply is to hit save and calculate. You can look at how quickly we're able to generate toolpaths for such kind of parts inside SolidCAM's new functionality. Let's click on Simulate. We have already done that. Let's go to the HostCAD and run the HostCAD simulation. You can see how nicely it has done the machining. One way, goes all the way up here, cuts the entire part and comes back. So it's a very clean tool path. And remember that we also had selected the fillet as one of our geometries. In most of the impellers, selecting fillets creates more problems than giving you a better solution, because a fillet is supposed to have different normal directions. They start from one direction and they finish on the other side. So it's very difficult to incorporate fillets inside the geometry unless and until it's a special application. So you can see that we have incorporated fillets also into the blade geometry, which makes it much more easier for us to program, including the fillets. Okay, let's finish the bottom floor. So I'll hit the Multiblade. I'll go to the hub finishing. In the geometry, I'm going to select this entire thing, because now I'm going to finish the floor between these three blades, including the splitter. And the hub surface is that one. I don't need exactly the same area, but I would like to keep about 0.1 millimeter on the blade splitters and fillets, because I don't want the tool to touch already the finished area. The tool remains the same. Levels, automatic, toolpath parameters, I would like to keep about 40 cuts on the surface. Sorting, I would like to do a zigzag starting from the trailing edge, and I'd like to go left to right. You have got options to go from left to right, right to left, from center away climb, center away conventional. So let's go left to right. Tool axis control again as default. Gauge check is default. Save and calculate. Okay, it's done the calculation. Let's show the toolpath. You can see very nicely it has done the hub finishing. Very neat, no much issues. Nice toolpath, minimum input. So what it shows with the new functionality in SolidCAM is that you could get high quality results with minimum input and minimum effort. These are what our new dedicated applications do for such kind of parts. Right, let's now finish this entire part using the fillets. We're going to finish the fillets. Multiblade, we're going to do the fillet finishing. And here in this case, I'm going to select only one portion because I want to just finish the fillets of the main blade. Okay, the hub here is that surface. And the tool also is going to be the same. You can change the tool, levels is the same, and toolpath parameters is something different here. We've got by number of cuts. I'm going to trim on the trailing edge because I don't want it to run completely around the blade, just the blade surface, not the side surface. I want about 5 cuts to come from the blade side, and I want to have about 4 cuts coming from the hub side. In total, I have 9 cuts, and the distance or the step over between the cuts is about 0.5 millimeter. Surface quality, sorting. Here I can be very careful. I can tell. I can go from top down, bottom up, inside outside, or outside to inside. Let's do the outside to inside machining because I want it to gradually come into the center. Edges again is automatic. Tool axis control, the default values work fine. Link, automatic. Gauge check, automatic. I'm going to hit save and calculate. It has calculated the toolpath. Let's look at how the toolpath looks like. Very nice. You can see that the entire fillet is now machined using this technology. The first cut will be from outside, then it comes to the blade side, then it again goes to the hub, comes back to the blade, and as it goes on doing this, it converges to the center of the fillet, thereby finishing the fillet. Because why this function is given? Because in practical cases, in case of impellers which are done, the bottom fillet generally is never of a constant value. It's basically a variable fillet, which cannot be done when you're doing the blade finishing. It needs to be handled separately, and that's why this function has been given in SolidCAM. Okay, let's move to another area, and that's trimming of vacuum form parts. You can see how quickly we can do the trimming. You can also control the axis of this trimming tool easily. So let me switch on the part. Right. So we have this part out here, which is mounted on a holding fixture, and we are supposed to trim the outer edge of the part. Because in vacuum form parts, you can't get this edge. This has to be done using a milling process, a 5-axis milling process. It's also same for some aerospace formed components which are done on a sheet. They have to be trimmed. Why they need to be trimmed? Because this surface or this area has to be very nicely done, because it matches to another area. There has to be no gap happening between the part and the other surface on which it's going to mate. So what we have in vacuum form parts, we have got contour 5-axis milling, wherein I don't actually need any surfaces. I can simply go to the geometry and select my curve along which I'm going to drive my tool. Sorry. Just select the edge. Okay. Perfect. This is the edge that I'm selecting. Okay. It's made up of a lot of bits and pieces. Perfect. So that's what we have done. We have selected our edge. Okay. Now, I also need to find out what is this thickness so that I can push my tool so much inside. It's about 2.5 millimeter thick. No problem. Now, how do I control my orientation of the tool? The orientation of the tool is controlled by orientation lines. Now, these lines could be a sketch that you have defined. For example, I've defined a sketch here, out here. And these orientation lines need not be normal to the outer surface. They could be following a certain pattern. For example, at this corner, I have some fixture out here in the corner, and I don't want the tool to continue rolling normal to the surface. I want the tool to lift up so that it clears that particular obstacle and then comes down back again, becoming normal to the surface. So these curves are going to control the orientation of my tool axis. So already I think I have, not this one, yep, contour 6, this is the orientation lines. I'm going to use a 6 millimeter end mill. Levels, plane height is 50. Entry safety and exit safety is what I again need to change, about 5 millimeter. In the toolpath parameter, all I need to define is what I want to do, on which side I would like to cut. Okay. Let's go to the tool axis control. The side tilt again, now we are coming back to our old tool axis the way it was, and I would like to give a side tilt of 90 degrees because I want to use the side of the tool to cut, to get into this part and cut the part for me. Okay. What I can also do is I can provide an axial shift, which means I'm going to push the tool into the part by about 2.7 millimeters. That means 0.2 millimeters more than the thickness of the part. Perfect. Okay. Everything else is okay. I just hit save and calculate. The toolpath has been calculated, and this is how my toolpath looks like. You can see that it's pushed inside by about 0.2 millimeter. Right. Let's see how the simulation looks like. Let's run the simulation. And if I go into the step-by-step simulation, that's the tool entered inside, and it's now following exactly those curves, the tilt curves that it's supposed to follow. Nice. And you can see that it's rotating around that area to the end. And as it comes here, I'd like to do a, let me go to the side view here, because I want to show you how it aligns itself to the different curves here. Okay, it's aligned to that line, and as it goes up and comes closer to this line out here, the line that has gone below, you can see that as it goes closer, it's aligning itself to that particular edge or that particular line. Now it's perfectly aligned at that point along that line. That's nice. And as it goes up, again, it's coming back to its original tilt. And as it comes to the corner, you can see what is going to happen in the corner, because in the corner I've got two lines with different tilt. So it's going to lift up and try and become, okay, there it is. That's that position. And then it's going up again and rotating. It's following that curve. So you can see that it lifted up, and as it negotiates that area, comes back again. Okay. Back again, following the same tilt lines. Perfect. That's it. So what this does is basically it allows you to program your vacuum form parts or trimming parts very quickly. And you really don't have to depend on the surface normals, because in many cases the surface normals are not the way to cut it, because you have holding fixtures that are holding the part below. You don't want the tool or the head to go and crash into the holding fixture. You want to control the tilt, and the tilt lines are the best way to control the tilt very easily. We didn't pick any kind of surfaces. We just picked the curve and the tilt lines, and we have a result. Right. We'll open the last part, and I want to show this part because of some nice functionality that we have inside SolidCAM. It's nothing new, but greatly improved functionality. I've got this extruder that you can see on your screen now. I have this extruder, and I would like to machine this extruder now in 4-axis simultaneous. If you look at the surfaces look very nice, but if you closely analyze it, they are of different widths, they're starting at different points, and they're ending at different areas. So deciding on what strategy you want to apply for this, it's going to be very difficult. Instead of that, I would like to cut this as one single area. How do I do that? Because there are multiple surfaces. What I have to do simply in SolidCAM is to make a dummy surface. For example, I've created this elliptical surface inside. And I'm going to use the 4-axis machining. Let me add geometry, drive surfaces. I already have them. Okay, that's the drive surface. Okay, the start edge, I'm going to use a morph between two curves, and the end edge is contour 1, the other side. Start and end at the exact surface edge. I'm going to use a 10mm ball nose. Levels, It's going to be a cylinder parallel to x-axis of 150 mm. Entry safety distance and exit safety distance of about 10s. Toolpath parameters, I want 2 mm side step, and I want spiral cut. Tool axis control, I'm going to use a default, I'm not going to change anything. I'll hit save and calculate. What it is now going to do is it's actually going to machine only that elliptical surface at the bottom. But that's not what I need, because I want to machine the surface above them. So what I'm going to tell SolidCAM, I have this toolpath, okay? I'm going to go back and I'm going to use the gouge check. And I'll tell SolidCAM that I have got surfaces that need to be checked for gouging, which are above the elliptical surface. And these are the surfaces. Sorry, yeah, these are the surfaces on that. Yeah, these are the surfaces. I'm asking SolidCAM to check these surfaces with the toolpath that it has already generated. And what it needs to do is to simply retract along the axis and keep doing that unless and until it doesn't find any, it finds no more gouge on the surface that we just selected. Let me hit save and calculate. Okay, it's almost done. It's doing the collision check now. Okay. So what it did now was to take the toolpath from that ellipse and pull it up all the way up to the surface of these surfaces, so that we no longer have any gouges. So you can see what has happened now here. It's pulled the toolpath all the way up to that surface. And how does this tool move? It's actually going to follow, the tool is going to follow the surface below for motions, but it's actually going to cut the surface above it. So the shape of that surface below will influence the tool movements above it. So using this method, you could have even small bits and surfaces, or the best part is you could have the upper area as an STL geometry, and you could machine that STL geometry in 4-axis without having to create any surface. So this is one of the nice functions inside SolidCAM's 5-axis module. All right, that brings us to the end of the first part of our webinar. We will continue this webinar next week at the same time with another application, another parts, very, very nice parts and nice applications. If there are any questions, you could type your questions, or you could raise your hands and we will answer your questions. Or the best thing is this particular webinar is going to be recorded. It's going to be available on the website. You could even download this webinar, which is going to be like a movie. Aya, I am done.
Okay, well, thank you very much for your presentation. Let's see if we have any questions. I don't see that anyone has any questions. Okay, so thank you very much. And like Amod said, the second part will be presented next week. And we are looking forward to seeing you then. Have a nice day. Goodbye.